In April 2026, a rocket tore through the lower atmosphere, carrying 4 people out of Earth's close orbit. This was Artemis II, a crew flying the Orion spacecraft on a free return trajectory, using the moon's gravity to slingshot back home. It marked the first time human beings had traveled into deep space since the Apollo 17 mission in 1972. The crew pushed further into the void than anyone before them, reaching over 252,700 miles away from our planet. Setting a new distance record is a milestone, but the sheer economics of doing it forces us to ask if sending humans that far out is actually a smart investment. This chart compares the budgets of different space programs. On the left, we see the massive financial input required for the Artemis program, an estimated $93 billion for a 10-day flight. On the right is a flagship robotic mission like Mars Perseverance. It costs roughly $2.7 billion. The disparity is massive. A single, short-term human program costs dozens of times more than an autonomous rover built to last over a decade on another planet. So we have to ask, what operational value are we getting to justify the astronomical premium of sending biological humans into space? To answer that, we need to strip away the emotion. We have to look at a strict return on investment, weighing the raw scientific output against the massive financial and biological inputs required. The primary operational advantage of a robotic mission is what it leaves behind. There is absolutely zero biological life support on this deck. Without the need to carry any food, water, waste processing systems, or heavy safety redundancies, the launch mass drops drastically. As a result, you get continuous data collection in extreme environments, like lava tubes, with zero risk to human life. This map shows the major trade-off to that baseline, the bottleneck created by relying on radio wave communication. Signals take about 1.3 seconds to reach a machine on the moon, and up to 20 minutes to reach one on Mars. Because robots follow pre-written instructions, that delay makes it impossible for them to react to sudden hazards or improvise on the spot. Robots give us unmatched endurance and data gathering efficiency, but in a crisis, they offer zero adaptability. Putting people in space requires a totally different scale of hardware. To put it in perspective, the Orion capsule and the SLS rocket needed to lift 78,000 pounds of mass off the pad. That weight comes directly from biological necessities. You have to launch 189 menu items, heavy water systems, and heat shields built to withstand 2,750 degrees Celsius on re-entry. The output of all that investment is immediate, real-time decision-making. Astronauts can execute manual thruster control and fix problems the second they happen. We've seen how human hands save missions. When the Hubble telescope needed critical repairs in 1993, astronauts physically replaced the failing components in orbit. But that extreme capability comes with strict time limits. Because of the immense and incredibly heavy resource drain, the entire Artemis II mission was strictly capped at just 10 days. The crew also absorbs intense physical risks, enduring high radiation exposure and the demanding effects of microgravity on their bodies. The human premium buys immediate adaptability and problem-solving, but you pay for it with an astronomical financial cost and high physical peril. During its flight, the Artemis II capsule functioned as a high-stakes experimental laboratory for human physiological endurance in deep space. Studies like Archer actively monitored the crew's movement and sleep patterns, mapping exactly how the body degrades away from Earth. During these highly complex flights, a massive percentage of the scientific effort is spent simply keeping the human crew alive, rather than studying the environment outside the window. Real people took on this specific biological risk to gather that internal data. Human spaceflight operates as a strategic investment. We must learn exactly how to survive the hostile environment of space before we can even attempt any long-term expansion. This flowchart breaks down the different mission paths. Humans and robots are not competing for the same job. They are entirely different tools. If the goal is pure scientific yield and resource testing, robotic missions are objectively superior. They serve as the vanguard, taking the initial measurements and mapping out the resources required for a permanent base. But if the goal is preparing for a sustainable presence on the Moon or Mars, human missions are mandatory. Robots execute the routine, multi-year science. That lays the groundwork for humans to perform the high-stakes viability testing. Which brings us back to the core question: is a $93 billion price tag justified by the returns? The Artemis budget functions as a mandatory expenditure for a biological proving ground. Validating complex life support, testing the heat shields, and measuring psychological endurance simply cannot be outsourced to algorithms. There is also an unquantifiable metric that robotics lack. Seeing real people out there provides a cultural return, inspiring the next generation of scientists. The true ROI of Artemis II is the specific, real-world data on human survival that robotic sensors cannot provide. Establishing a sustainable footprint in deep space requires this initial premium, paying for the safety of the people who will eventually